Hello everyone and welcome back to VisualLab demo videos. In this video we are going to do a 4-bit ripple counter or a 4-bit asynchronous counter. You have to search on Google at vlab.co.in, vlab.co.in. Okay, then you will get this page of MHRD. Okay, you have to select Electronics and Communication here and the Digital Electronics Lab by IIT Roorkee. Okay, click on that link. Then you will get this page of IIT Roorkee. There you can see the list of experiments. Click on that link. There, the 10th experiment, design and verify the 4-bit synchronous or asynchronous counter using JK flip-flop. Click on that. You will get into that experiment. So our experiment name is design and verify the 4-bit synchronous or asynchronous counter by using JK flip-flop. And the aim of the experiment is to verify the truth table and timing diagram of a 4-bit synchronous parallel counter and 4-bit asynchronous parallel counter by using JK flip-flop IC and analyze the circuit of 4-bit synchronous parallel counter and 4-bit asynchronous parallel counter with the help of LED display. Move on to the theory, explaining what is asynchronous counter, what is an asynchronous counter, and then what is the design of a 4-bit synchronous and 4-bit asynchronous counter. So, what is a counter initially? A counter is a device which stores the number of times a particular event or process has occurred, often in relationship to a clock signal. Okay, counters are used in digital electronics for counting purpose. They can count specific events happening in a circuit. For example, in a counter increases count for every rising edge of the clock. Okay, then the classification of counters. Counters are basically classified into two categories, that is asynchronous counters and synchronous counters. Now, what is an asynchronous counter? In asynchronous counter, we don't use universal clock. Only flip-flop is driven by main clock and the clock input of the rest of the following counters is driven by output of the previous flip-flop. You can understand by the diagram. Okay, here we have 4 flip-flops. JK flip-flops are used 4 flip-flops and a high input and a clock pulse. Only in the first flip-flop we are giving the clock signal, and for the rest of the flip-flops we are feeding the output from the first to clock input of second, and the second output to the clock input of third, and the third output to clock input of second. So it is known as an asynchronous counter. We are giving only the clock signal for the main clock for the first flip-flop. Okay, then the clock signal will be like this, and the Q0 JK, this high signal. So Q0 will be like this, and Q1, Q2 and Q3. This is the timing diagram. And when the Q0 is changing, as soon as the rising edge of clock pulse is encountered, and Q1 is changing when the rising edge of Q0 is encountered, and so on. Okay, so this Q0, Q1, Q2 is also known as a ripple counter. That is our experiment. We are going to do a ripple counter. So we can move on to the simulation. Click on the simulation link. There you have 2 links, asynchronous counter and synchronous counter. Click on the asynchronous counter link. Okay. So this is a 4-bit asynchronous parallel counter using JK flip-flop. This asynchronous counter is also known as a ripple counter. So this diagram or the circuit is inbuilt here. We just need to click on switch on the power supply and give the trigger or give the clock pulses. Then we will get the truth table here. So this is a 4-bit counter. So we have numbers from 0000 to 1111. Okay, that's 16 pulses we have to give. So switch on the power supply, click on the switch, and it is 1 now, that is the switch is on. Okay, now we are triggering the circuit. You check on this output. This is our output Q0, Q1, Q2 and Q3. These are the outputs. Okay, this diagram or the experiment is done by using IC7476 IC. Okay, then this is the 7476 is an IC for JK flip-flop. Each IC contains 2 JK flip-flops. Okay, so we are using 4 flip-flops here. So we needed 2 ICs here. 2 7476 ICs and the connections are done here. We just need to switch on the power supply and trigger the clock pulse. Okay, so it is a negatively triggered clock. What does it mean by negatively triggered clock? When the trailing edge of the clock occurs, the change will happen for the output. Or when the trailing edge means negative going clock pulse. For the negative going clock pulse, we will have a change in the output. Okay. Now we are changing the clock pulses. Click on this clock. Okay, first clock. We are giving the first clock. So clock number 1 and our output is 0000. We are counting for the first time, that is 0000. We are giving the second clock and the count is 0001. Third clock 0010, fourth 0011, fifth 0100, 6 0101 and 7 0110, 8 0111. That is on 8th clock, we are getting the number 7. We are counting to 7. On 8th clock, we are counting to 7. Okay, from 0 to 7. 8 clock pulses are there, but the number is 7. Okay, then clicking on 9, 1000, 10 1001, 11 1010, 12 1011, 13 1100, 14 1101, 15 1110 and 16 1111. Okay, now we have arrived at the last numbers 1111. That is our last number on the counter, and you check on this, our counter, all numbers are active now. All LEDs are blown now, and we can generate the waveform. Click on the generate waveform. Okay. They generated the waveform. You can see here, this is our first clock pulse. From this to this is our first clock pulse. On the trailing edge of this clock pulse, our output is changing. Okay, output is 0 first. On the trailing edge, we are getting the output as high. Okay, the output is changing on the trailing edge or the negative going edge of the clock pulse. That is, it is known as negatively triggered clock. Okay, on the negative edge of Q0, this Q0 is fed into Q1, input of the second flip flop. That is, on the negative edge of this Q0, we have getting the changed Q1 output. On the negative edge of Q1, we are getting Q2. And negative edge of Q2, we are getting Q3. So this is the waveform of a ripple counter or a synchronous counter, and this is the truth table of this counter. Okay. Here you have print option. So click on print, and you will get the truth table, the waveform and the circuit, everything. Then click on print and save it as 4-bit ripple counter. Okay. 4-bit ripple counter. So the ripple counter experiment is done now. If you like, you can go to the previous one and check the synchronous counter. Before that, you have to move to the theory of a synchronous counter. What is a synchronous counter? Okay, the synchronous for the synchronous counter, we are giving a global clock. They are saying that is each flip flop is powered from only one clock input. This clock input is fed into every clock input of flip flops. Okay, and we are taking these outputs. So this will be the timing diagram of the synchronous counter. So we can move on to the simulation. In this simulation, we are using the same IC 7476. One IC have 2 JK flip-flops. We need 4 JK flip-flops. That is, we are using 2 ICs here, and we are getting the outputs here. So switch on the supply and give the triggers. 0, 1, 2, 3, 4, 5, 6, 7, 8. You can see here the LEDs are blinking. 9, 10, 11, 12, 13, 14, 15, and 16. Okay, up to 1, 1, 1, 1 we have counted. You can generate the waveform. Here also, on the negative going edge, we are getting the output. On the negative going edge, we are getting the output. Same. Okay, now you can click on print. And save this. Save this as 4-bit synchronous counter. Okay. So that's all about the synchronous and asynchronous counters. We have on syllabus the 4-bit triple counter. So you focus on a 4-bit asynchronous counter. Thank you.